The archer shoots an arrow with some initial velocity and height, and we are tasked with predicting whether or not she will hit her target. The initial velocity can be thought of as a vector quantity, meaning it consists of a magnitude, in this case the speed, and a direction. In this case, the direction is represented as an angle. We sometimes call projectile motion two-dimensional motion. The flight path of the arrow extends in the horizontal and vertical direction, but not into or out of the screen as seen from this perspective. In that sense, we say that the flight path of the arrow occurs in a plane. We can adjust the initial vertical position of the launched arrow by adjusting the posture of the archer. She can be standing, kneeling, or crouching. Looking carefully at the graph at right, we can see that the initial vertical position of the arrow at time t equals 0, represented in blue, increases and decreases as we adjust her posture. As you can see, if you look at the blue line at later times, the arrow goes up and then goes down. We see its vertical position increases to a maximum and then decreases after that. The slope of the blue line at any point in time represents the vertical component of velocity of the arrow at that same time. The slope is initially positive, then 0 at its highest point, then negative after, meaning the arrow is coming down. The green line here shows the horizontal position of the arrow as a function of time as well. Since the arrow is moving rightward at steady speed, it just looks like a line with constant slope. The slope of this line represents the horizontal component of the velocity of the arrow. Since this slope never increases or decreases, we say its horizontal velocity is constant. This is actually a bit unphysical. A real arrow would slow slightly with time due to drag with the air. But this model isn't terrible. The graph at left shows the horizontal and vertical components of velocity, again as functions of time. The horizontal velocity, shown in green, stays constant throughout the flight, as we've discussed. The vertical velocity starts positive, descends to 0, then goes negative as the arrow starts to come down. In this case, the slope of the left-hand graph represents the acceleration of the arrow. The horizontal acceleration is the slope of the green graph, 0 throughout. The vertical acceleration is the slope of the blue graph. Here you see a constant downward slope. This is the acceleration due to the force of gravity. As you can see, the vertical velocity decreases by about 10 meters per second over the course of a second, exactly what we'd expect. The initial values of horizontal and vertical velocity, the values at time t equals 0, are determined by the initial speed and angle of the arrow. Standard trigonometry formulas apply. The initial horizontal velocity, the value of the green line on the graph at left, is equal to the initial speed multiplied by the cosine of the launch angle. The initial vertical velocity, the value of the blue line on the graph at left at time t equals 0, is equal to the initial speed multiplied by the sine of the launch angle. You can use this simulation to set up and solve your own problems. Decide on a launch angle, a target distance, and a crouch height, and predict the speed you'll need to hit the target. Hope you have fun with this.